Okay, welcome everyone to the Hot Electronic Seminar Talks. I'm hoping you're joining us live, but if not, I certainly welcome you on YouTube. Let's see, just a couple of reminders. It's not the first talk, so please keep your videos on during the talk, and please keep your mics muted. We're going to have a 1-hour talk followed by up to 30 minutes of discussion. And I think that's about it. So without further ado, I'm going to introduce our speaker today, Joachim Kock of Universidad Autónoma de Barcelona, who will speak about infinity operads as polynomial monads.
Thanks a lot. I'm excited to be here in the electronic seminar. It's the first time I try anything like this, so let's see how it goes. I was a bit worried that I would have to do a Beamer talk because I never did that in my life, but now I figured out how to avoid it by writing on this little bit of blackboard here live. I've tried this in mathematical discussions before, but that's only with one person. Now there are more persons than one, so you should just stop me if I begin to write too small. But that's just like a blackboard talk. You have to stop the speaker many times during the talk, telling him that he writes too small. Okay, so let's begin. As infinity operads as polynomial monads, and this is joint with David Gepner and Rune Haugseng. Now I'm already finding the paper very small. Okay, so the idea is, if you look at this square, that you have ordinary categories here. So that's 1 in, 1 out. And then you have ordinary operads, which is many in, 1 out. And then here we have everything is overset. And now we pass to do everything over spaces. So this is spaces. And then you get, of course, infinity cat. And what you get down here is infinity operads. So that's what I'm going to talk about and explain how it can be done with polynomial monads. And I think the justification for talking about this in this seminar is that polynomial monads are things that type theorists like for several reasons. Well, let me come back to that. Okay, so by infinity categories, that means quasi-categories, but it could also mean other models like Segel spaces. And in this talk, Segel spaces will maybe play a bigger role than quasi-categories, as you will see. There are many different models for infinity operads. So the most developed theory is the one by Lurie, but I'm not actually going to talk about that. So the idea is exactly to exhibit a new model for infinity operads, which will just be polynomial monads. Okay, now I have to figure out where to put this and continue. So let's start with operads. Since Max Kelly 72, you can think of operads as monoids in symmetric sequences. So what's a symmetric sequence? Well, it's first of all a sequence of sets or spaces, classically sets, and they all have symmetric group actions. And then you need a certain monoidal structure, which is composition, and you need a unit. And then this is a monoidal category, and you can talk about monoids in there. So what's the monoidal product? Well, if you have two sequences A and B, then you can define B circ A. And then you need to say what are the n-ary operations of that. And that is, you sum over all maps from N to K. Then you look at all the, so for each point I in K, you look at the fiber and call it Ni. So that's N1 times up to Nk, and finally Bk. And then you need to divide out by automorphisms of this map. That's a detail to make it correct. So this defines the monoidal structure on symmetric sequences. And now you just look at monoids in here, and you get the usual notion of operad. So
is each AN a space, and there's a symmetric group action on each?
Yes.
Right?
Okay, now this is the same thing as species. So a species, so that's Joachim 81. A species is a functor from the category of finite sets and bijections into the category of all sets. And you think of it as saying F tells you all the possible F structure you can put on a finite set N or S. So you denote it like this. So this was introduced by Joachim as a model for power series, and to give like a combinatorial model for all the manipulations you do with power series. And the main point is that given such a species, you can associate to it a series, GF, and it's the series where you put the cardinalities of all these sets of structures, and then you put, set to the n, that's a set, and then you divide out by n factorial. So that's like the generating function for these numbers. And the point of the definition of Joachim is that if you take the generating function of, there's a composition product for species which is denoted like this, G applied to F. And if you take the generating function of that, that's the same thing as taking the generating function of G and the generating function of F, and then composing them like power series. So the substitution product for symmetric sequences you see here, that's the same as the substitution product for species that is a model for substitution of power series. And now you can say that operads are monoids in species. Now you can do more, because if you have a species F, then you can look at its left Kern extension along the inclusion here from B to Z. Notice that this is not full, because here we only have bijections, here we have all sets. So when you take now the left Kern extension here, F bar, then you can write down a formula for F bar, and it is the following. It takes a set, and then it's sum over, well, it takes the species applied to n, and then it takes x to the n, but then you divide out by the action of the symmetric groups here. And you can see that this is the format of an analytic function. that you sum, you divide by some factorials, and you have some coefficients. So in this case, in this sense, this is called an analytic functor. So analytic functors are species is a model for power series, and the model goes through this notion of analytic functor, because now you can see that this notion of power series from before, it's just to take cardinality of this analytic functor. So now there's a equivalence of categories, so that's also Joachim, between species and analytic endofunctors. And now we can say, since the composition here corresponds to a composition of these functors, we can now say that operads is monoids in analytic endofunctors, and that's to say they are analytic monads. So this is the starting point, that you reinterpret the notion of operads as being analytic monads. Now, Joachim also did something more. He characterized the analytic functors. So a functor, an endofunctor of the category of sets is analytic if and only if it preserves filtered colimits. So that's clear just from the definition of a left-Kahn extension along this inclusion from finite sets to sets, and it preserves wide pullbacks, but only weakly. So wide pullbacks, well, if an unusual pullback is just a projective cone over this, a wide pullback is the same thing with infinitely or possibly infinitely many legs like this. So what does it mean to preserve wide pullbacks weakly? Well, it means that if you stick in a wide pullback here and you look at its image, it will not be a pullback, but it will be a diagram that has the universal property of the pullback, except that the map that should be unique is not required to be unique. And the reason it's only preserved weakly, that's because of problems with colimits in the category of sets. So if you are a classical category theorist, maybe you are used to thinking of the category of sets as the most perfect category that all other categories would like to be like. But it turns out that many colimits in sets are not really nice. And the one that's not nice that enters here is if a group acts on a singleton set, then the quotient is just a singleton again. This is an example of a colimit, and it's a really bad colimit. It does not have good properties, and in particular, it does not behave well with pullbacks. So another example of a very bad colimit is a push-out like this. If you take a two-element set and you map it to one-element sets like this, and you take the push-out, you get just a one-element set. And that's another very bad colimit. So somehow the whole justification for upgrading category theory to infinity category theory is to correct these bad pullbacks. These bad colimits. Yeah, maybe I don't want to say too much about that, but this weekly will go away in just a few pages when we come to the infinity case. Okay, now we come to polynomial monads. Oh, that's funny. This is page 4, but so there are 2 pages 4. So this is 4b. So polynomial functors. So if you have a map of sets from E to B, then you build a functor that does the following. It takes x to, first you sum over all the elements here, and then you take x to the EB. And EB is the fiber of this map over small b. So this is called a polynomial because it's a sum of monomials. But notice, however, that it may be an infinite sum, and that actually the fibers of this map might be infinite. So some people don't like the name polynomial, but now they're called polynomial. So finitary, well, finitary should mean that it preserves filtered colimits. And this happens if and only if P has finite fibers. So if we restrict to finitary polynomial functors, that means that this has finite fibers. And now these are special cases of analytic. They are those for which the symmetric group actions are free. Or you can characterize them as those that preserve wide pullbacks strictly. So that means that they are much better behaved than arbitrary or general analytic functors. In terms of species, they're, well, in combinatorics they're called flat species, but that just means it's another word for saying that they're species where the group actions are free. Now, polynomial monad, that's of course just polynomial endofunctor with a monad structure. These are the sigma cofibrant operads. It doesn't matter so much now what this means, but they have played an important role in the development of the theory of operads. And it is just the same again, that the symmetric group actions are free. Okay. Now we should go to many variables. So now the polynomial functor is given by a diagram like this. S, P, T. And maybe I should go back to the previous paper here and just put the one variable case means that there's just a 1 at the ends here. But putting it in this way is nice because then you can write this in the following shape. First you do pullback along S, then you do lower star along P, that's right adjoint to pullback, and finally you do left adjoint to pullback along T. So if you unpack what all these adjoints do, then you get exactly this one. Now this formula generalizes precisely to the many variable case. So now you get a functor from the slice over I to the slice over I, and it takes a family like this and returns, well, pullback along S, lower star along P, and lower shriek along T. And here you have to put this. And this is where possible interests from type theory may come in, because these are the categorical versions of dependent sums and products. So this is like dependent product, and this is like dependent sum. So if you take such a family here and you write it as a dependent family like this, and if you unpack all these adjoints, then it does the following thing. Well, it's going to give a family indexed over here, so it goes like this. And what do you do? First, you sum over the fibers of this map, so that means you sum over this, and then you take the products of the fibers here, like that, and then finally now you have something over E, and you take pullback. That means substitution of the indexing here, so here you do S of E. So this is the spelled out in family notation of what this polynomial functor does. And these are literally dependent sum and dependent products of dependent families.
Sorry, what does the SE mean?
SE. So E is now an element over E here, and you just map it down here.
Oh, okay.
So X starts life here. And making this pullback, that means that you are taking the index of here and mapping it down here and see what the fiber is. Okay? Okay, so this is many variable polynomial functors, and they do like this, and of course you can put monad structure on them and have many variable polynomial monads on these slices. If you go back to operads, then these are colored operads. So if before you look at an operation and you picture it like this, now you would have to decorate it with colors. So the color set is I. That means that you decorate all these input slots with elements of the set I, and also the output slot is decorated by a color. So example, a small category is the same thing as a colored operad with only unary operations. So when you picture an arrow like this, it goes from I to J, and the arrow is called B maybe. So colored operads generalize at the same time usual operads and small categories. Okay, now I just need to situate myself in my plan. Now we should go to infinity. So intuitively, infinity categories are like weak category objects in spaces. Or maybe you want to say enriched in spaces. So this is spaces. And what does spaces mean? Well, spaces means infinity groupoids. So one way of thinking of infinity categories is first to pretend you know what infinity groupoids are, and then you're just looking at weak category objects in there. But if you don't want to do that, then you can use currently the best model, which are the quasi-categories. And although the definition is not due to Joyal, the whole theory is. but you should also see higher topo theory of Lurie. So there are certain simplicial sets, but they play no role in this talk. So another model, which is more important now, are the Segel spaces. So they are more faithful to this intuition. So that means that a Segel space, it's a simplicial space, and it's required to satisfy the Segel conditions. And what are the Segel conditions? Well, in any simplicial object, there's a canonical map where you project onto the principal edges of a simplex, and you demand this map to be an equivalence. So that's the definition. So if you do this with sets instead of spaces, this is one characterization of categories among all simplicial sets. There are those simplicial sets for which these projection maps are, in that case, bijections of sets. So this is the model for infinity categories that we will take as starting point now that we want to go to operads. So in the passage to operads, let me just note.
Sorry, Joachim, do you care about the completeness condition? And if not, why not?
I don't, because it does not play any role here. So later on I will define, well, I will not, well, let me come back to that. It plays no role. That's the answer. Okay, the note I wanted to make is just that you can look at delta as the linear trees. So that means that the object 0 you picture like this, the object 1 you picture like this, object 2 you do like this, and so on. So this is the clue for how you now pass from infinity categories to infinity operads. So infinity operads. Well, I should mention Lurie's model here, but I do it in a parenthesis because I'm not going to use it. So there are certain vibrations over the opposite of the set of category of finite pointed sets. And then I put some suspension marks here because I don't want to give this definition. It's currently the best developed notion of infinity operads, but there are other models, and the one I want to use is the following. So that's the Szysinski Moerdijk dendroidal Segel spaces. So what is it? Well, you start with a category of trees. And then you look at pre-sheaves on that with values in spaces. And then you put a kind of Segel condition. And let me make a picture of this Segel condition. The condition says that the value of a pre-sheaf on some tree, like this, it should be equivalent to the value you get when you restrict to each node. So here I just look what happens locally here. Oops. Here I look what happens locally here. And finally I look what happens locally up here. And then they should, of course, agree. So this is a fiber product over this edge here. And this is a fiber product over this edge here. So this is a picture of the Segel condition. that the value of x on a tree should be determined by its value on the elementary trees, subtrees of the tree. So elementary means either it has only one node, like these, or it has no nodes, like what you glue along. So these correspond to the objects when you look at the usual Segel condition. Okay, so this is another approach to infinity operads. They are pre-sheaves on the category of trees that satisfy a Segel condition. Now there are theorems to compare all these models. And this is Szysinski, Mordijk, Heutz, Haugseng, Chu, Hinisch. There are many models, and they have all been compared. So it's a whole zoo of different models of infinity operad. However, none of these has the feature monoid in symmetric sequences. So you could, if you go back to the starting point of my talk, I talked about monads and symmetric sequences. But none of all these models have that. So that's the new model. That's with Rune and David. Sorry. We define infinity operad to be analytic monad. So first you need to make sense of this, and then if you want anybody to pay attention, you should also prove that this notion is equivalent to one of these. So that's a theorem that this infinity category of analytic monads is equivalent to, and here I write dendroidal Segel spaces of Szysinski and Mordijk. So these are dendroidal Segel spaces. Okay, so now I have told you the main result. Now I want just to explain you the rest of the time. How does the theory of analytic monads look, and maybe give a little bit sketch of the theorem. So the point is that this theory can be developed inside the theory of polynomial functors. This theory develops as expected. So that means that you look at diagrams of spaces like this, and you define functors, and you prove all the same things as you did for one categories. But of course, the proofs are often quite different. But the theory does have some new features. So let me just mention a few new features. Let me see. So one feature is that colimits are computed in pre-sheaves on diagrams of this shape. So diagrams of this shape, that means like this. This is new. This is not the case in over sets. So maybe you ask, if this is a pre-sheaf category, then you can always compute co-limits pointwise. Yeah, but it's not a pre-sheaf category because the correct morphisms, they look like this. If you have two polynomial functors here, the correct morphisms require the middle square to be a pullback. What does it mean? Well, B played the role of operations. So here you should think that you have to map an operation from this polynomial functor to another one. Then the fibers should have the same size. That's what it means to be a pullback. So if this operation is of arity 7, that means the fiber has cardinality 7, then the image of that operation should also have cardinality 7. So it's fundamental, it's really important that you only allow Cartesian squares in the middle. And once you start to put this kind of condition on a pre-sheaf category, then usually the co-limits change. And in particular, in the category of sets, they will change. But in the category of spaces, in this case, they do not. You can still calculate co-limits by doing it in the pre-sheaf category. And that's because the co-limits behave much better in spaces than they do in sets. So that's an important improvement, so that in a sense, the theory of polynomial functors over spaces is better than over sets. Of course, it's also more difficult because you need to work with infinity categories instead of categories. And many of the proofs become technical. Maybe I want a few more things. So if you fix a polynomial endofunctor and slice over it, then this is actually an infinity topos. This, I don't know if this is true. I mean, if I go back to the category of sets and ask if the slice is a topos, I don't know actually. It might be true, but it might also not be true. But it is true when you go to infinity and work over spaces, then it's not difficult to show that these slices are toposes. I think I had one more thing I wanted to mention. Ah, yes, of course. All analytic functors are polynomial.
Quick question. The definition of infinity topos is a localization of a pre-sheaf category, right?
Yes.
So what is the pre-sheaf category there?
We don't see it. I mean, in this case, the base topos is the infinity topos of spaces, and it's already a pre-sheaf category. You don't need to localize. This is also a pre-sheaf topos.
All right, don't worry about it.
Okay, why are analytic functors polynomial now? It's because in the infinity world, all group actions are like free. So some of the very bad things that happens in the category of sets, if I can find it, bad quotients like this, that happened because the action of G was not free. But in the infinity world, these quotients of course, it's no longer just a point, it's a classifying space of the group. Now they're well behaved, and that's what makes all analytic functors polynomial now. So this means that the main theorem that said that analytic monads is a model for infinity operads, that can be developed within the theory of polynomial functors. Okay, let me see. Okay, so proof ingredients. And I'm talking about the main theorem. First of all, it's a careful analysis of the construction of free monads. And then there's a tree description. And then finally, there's some nerve theory, a nerve theorem in the style of Mark Weber. So I would like to concentrate on this and tell you a little bit about how this looks and a new viewpoint on that. So there are 2 points there. Initial algebras, and then there are free monads. So I will talk quite a lot about initial algebras, and then we will see that they are used to construct free monads. So now we're looking at an endofunctor of an infinity category. Then a P-algebra is just a pair A, small a, where A is a map from PA to A. There are no axioms. And a P co-algebra, that's just the opposite. It's a pair CC, where C goes from C to PC. So if you want to define co-algebra more formally, you need to do like this. If you want to define this category, then you say, well, first of all, it should be an arrow. So you take an arrow. Then you return the 2 endpoints of that arrow, and you want to impose the condition that this C is the same as this C. So that means you put identity, and then you put P here, and then you take the pullback. So if you want to be formal, you define it like this pullback. Now comes a definition which is a bit funny in this context, but it has a long history in algebraic topology, and it's twisting morphisms or twisting cochains. So if you have a co-algebra CC and an algebra AA, a twisting morphism, it's a map in the underlying category from C to A, with the property that if you precompose with the structure map of the coalgebra, you compose with PF, and then finally A, this is commutative. So more formally, you can define the space of P-twisting maps from C to A. You define it as an equalizer. So you say it's those maps from C to A such that if you do nothing, or if you do this, so this is F goes to C, P, F, A, that should be the same. So you formally define this mapping space of twisted maps from C to A to be this equalizer. Now a small observation. If you have a coalgebra, and you apply P to it, then it's also a coalgebra. And furthermore, the canonical map that simply takes C itself is a coalgebra homomorphism. And now comes the first lemma, lemma 1. It says that the canonical map from twisted morphisms of this new coalgebra to the twisted morphisms of the old coalgebras is an equivalence. So what does it do? It takes a map G and then just precomposes with C. So let me write here again the diagram. So now we have G, it goes from here to here. To get twisting, you just precompose with C. That's the canonical map. And the claim is that this is an equivalence, and it's very easy to exhibit an inverse. The inverse take a twisting morphism from C to A, like this, and then we need a morphism from here to here. So you just take P of F, and then you compose with A. You can easily check that these are inverse to each other up to homotopy, so that we get this equivalence. Okay, now we begin to work towards initial algebras. And I think many of you have already constructed initial algebras by starting with the empty set, and then you just apply the functor as many times as needed, which may be omega many, and that will give you an initial algebra. So let's assume that C has filtered colimits and P preserve them. And let C be a coalgebra. So I do all this for a general coalgebra because we will see that it fits into cobar-bar duality, which is really nice to see in this context. But in the end, I'm going to take as coalgebra the initial object, if there is one. So what do? You take C, you go to PC, and then you go to P of C. And then you take the colimit of all that and call it I. Okay, now there's a map from I. So I is the colimit. And now I put an extra n that doesn't change the colimit, because now I will use the universal property of the colimit to go to here. And this is P of I. Now, because I assumed that P preserves filtered colimits, this is an equivalence. Okay, so therefore I get a map here called U, and now we define omega C to be I comma U. So this is now a P algebra, and it's called the cobar construction. And this is a functor from coalgebras to algebras. And later on we will put C to be the initial object, and that will produce the initial algebra. But there are some small exercises to do first. So now comes lemma 2. Lemma 2 talks about this situation where we have a coalgebra, in this case from I to pi, with the property that it's invertible, so that it's also an algebra. So in that situation, so if you have a coalgebra with U and equivalence with inverse V, and if you have an arbitrary algebra, then you can look at the following. You can look at algebra maps from this UV to the algebra. And the lemma says that these are modeled by the twisting maps. So, I mean, it's no surprise here. You just use the fact that U is invertible. And then you check that what it means to be an algebra map, if you look at V, is the same condition as what it means to be a twisting map if you use U. It's nothing deep here. But now comes the, well, maybe I will put it here. The proposition says that algebra maps from the cobar construction on a coalgebra into A is the same thing as twisting map from C to A. So that's the first important property of these twisting maps and the cobar construction. So later we will see that there's dually a bar construction that starts with an algebra and then produces a coalgebra, and that's called B. And then this will be also the map of coalgebras from C to BA. So in the end, the cobar construction will be left adjoint to the bar construction, and this is the adjunction. But the important thing here is that there is this notion of twisted map that realizes this adjunction. And in a sense, without mention of the cobar construction and the bar construction, it's just there in itself, and you can use this notion. Well, but for the moment, let's prove this proposition. Maybe I just write it here. A map from okay, the first step, well, theorem, proposition, well, whatever. The first is to use lemma 2 used on the cobar construction. It has this property. That means we can write the first step here as twisting morphisms from the colimit of P and C into A. So this is lemma 2. Okay. So now it remains to show that this is equivalent to just this. And the idea is easy. You just use the definition of the twisted morphisms. So the twisted morphisms were defined as the equalizer of these mapping spaces. So that's calling P and C A, and then the same thing here. the same thing. Now you take these colimits out, so it becomes limits. Whoops. Limits map PNC A, and then limit map PNC A. Okay, now the point is to compute this limit in a different way. And I like this proof because it's a kind of Fubini, that you commute limits with limits to compute that limit in two different ways. So here's how it goes. We'll make here a big diagram. So it starts in the bottom here. Maps from C to A, and maps from C to A. And now you start to apply the P. And then you go to the limit. That gives you limit PNC A and limit map PNC A. And what we needed to do was to take equalizer of these two maps. So that will give us here limits twist P, PNC A. Okay, but now we compute this limit in a different way. We can compute it first by the rows. So the diagram is this. Instead of computing limits here and here, we compute them row-wise and then take the inverse limits. So here, by definition of the twisted morphisms, this is just this. Here we do the same. But now, because of lemma 1, these are the same. That precomposing with the structure map does not change the twisted morphisms. Okay, that's, let me see if I have it easily. It's this one. That G is sent to precompose with C and F is sent to postcompose with A, while you have to apply P in the middle. So now this is an equivalence. Therefore, when you take the inverse limit of all these, you get the same thing. So therefore, these are the same. And that's what we had to show. Okay, so that's the proof of this proposition that maps out of the cobar construction are given by the twisted maps. Okay, now we have everything set up. Now we just apply it to a very easy case, namely, suppose that there is an initial object. Then this one is initial P algebra. And that's nothing but computing, because you take any other algebra and you want to compute the algebra homomorphisms from there to there. Well, by the theorem we just proved, this is the same thing as twisted maps from initial to A. So this is clearly contractible. So as soon as we do have an initial object, then we can construct the initial algebra directly. But now comes the nice thing that we can do this relatively.
Joachim, just a quick comment that technically you're out of time, but please continue.
Yes, so I filled this one, and that will already give.
Oh, no. Just do it the usual thing. Just keep in mind that, yeah.
Okay.
Short on time, let's call it.
Okay, thanks. Now we just relativize this. So if you start with any endofunctor like this, and for any object, then you can define an endofunctor on the coslice. And it goes like this. Oops. First you forget x, then you apply p, and then you just add up with x again. So this is the map that sends just add an x so that you become under x. So all this says is that this new map px, it takes something under x, and then it just returns this one. Okay, now we can, I promised to finish on this paper, but it's so small, so I need one more. I'm sorry about that.
Take two. How many pages do you have numbered?
I'm sorry?
How many pages do you have numbered?
30. But I promised
okay.
No, I numbered a lot because I didn't know, maybe I had to throw some of them away. But here's the theorem, and then I stop. The theorem says that the forgetful functor from algebras to C is monadic. So proof, well, first we have to give a left adjoint. And by the infinity version of an old result of MacLane, we just need to show that each coslice alg p c over x has initial object. But this coslice, well, you check easily that it's actually a true coslice, namely for this px. And this one does have an initial object because the coslice itself has an initial object, even if C did not, namely the identity. So you apply the Kobar construction to that, that gives you an initial object in the category of algebras. And that is the value of the left adjoint here. Well, you need to check it's monadic. That's the Lurie-Bar-Beck theorem. But the main point is really to construct this left adjoint, and it's given by taking initial algebra for the px's. So the monads that you now get on C is the free monad on P. I don't have time to explain why it's so important to have this free monad on P and how it enters in the proof of the equivalence with the Gödel Segel spaces, but it is the main point. And it's also what I think might be of interest to type theory, because when you pass from W types to higher inductive types, you would like to do free monads rather than initial algebras, as far as I understand Schulman and Longstein. Okay, so let me stop here.
All right, thanks a lot. I will now unmute everyone's microphone so that we can thank Joachim for the talk, and then move to questions. So here we go. Unmute all. And all right, I'm gonna move to mute all. Okay, that was arranged. So now we're going to start with, we're going to continue with the questions. So does anyone have any questions? Because I have a couple of my own, but.
Elaborate on Emily's question about the completeness of the Segel spaces.
So yeah, just in case you're muted. So so I can try to unmute you. Here we go. You're unmuted now. You hear him?
No. No.
Yes? Sorry. I know if you answered when we couldn't hear you, or...
No, I didn't hear the question.
Oh, the question was, can you elaborate on Emily's question? Was that the question?
Ah, okay, about completeness.
Yes.
Yes. Okay. Well, it's just because in the theory of dendroidal Segel spaces of Szyszynski and Mordijk, they don't put this condition. So if we want to compare with their theory, we should not put it either. But I confess we did not try. I don't know how big a role it would play. I mean, if I go back to the picture of the Segel conditions, and now I go back to the other camera. Here's the picture of the Segel condition. Completeness for completeness for dendroidal spaces only refers to the unary part. That's a unary part. That's all I can say. I don't know how it would affect the theory, or yeah, sorry, that's not much of an answer.
Should probably ask either Emily or Ali whether that addresses their questions. So if you guys have a follow-up or something. Okay, that doesn't sound like a question. Okay, can you actually finish as in the talk? How do the construction of a free monad enter in the proof? Because you gave the list of ingredients and then.
Okay, thank you for asking that question. The point is that there's one step more, namely that you can prove that. So if you let P bar be the free monad on P, then if P is polynomial, represented by a diagram like this, then P bar is also polynomial. And it has an explicit description in terms of trees. It has the same colors, of course. Now the new operations are precisely the P trees. And the polynomial diagram is like this. So these are P trees, and you can return the root color. These are P trees with a marked leaf, and you can return the color of that leaf. So using the inductive construction of the free monad, you extract this explicit description of it as a polynomial functor. And that is essential when you want to prove things about the Segel condition, because you really want to break things into trees. And that you use crucially that the free monad has this description in terms of trees.
And so that's the direct analog of the one categorical picture, right? With the P trees, or no?
So maybe an analog would be that if you have a graph and you take the free category on that graph, then what do? You take a sequence of composable edges. So these sequence of composable edges, they look like this. Here you put edge 1, here you put edge 2, edge 3. So they could go crazy in the graph, but they are, in the end, they are a sequence of composable edges. So that's like a linear tree that you map into your graph. And here you're just mapping general trees into your operad instead of, or into your polynomial endofunctor instead of mapping linear trees into a graph. So the analog is with the description of the free category on a graph in terms of linear orders.
I mean, what I meant is, so the picture with P trees that you have there, does the same regardless of whether P is well, it's a polynomial functor, like polynomial functor or polynomial infinity functor, right?
Yes.
Yeah. Okay. So that's because the theorem that you're stating now is the infinity theorem, but the other version for one category was known. So that's the only.
Yes. Somehow that goes back maybe all the way to Lambeck. I'm not sure, but it's definitely in Moerdijk and Palmgren. And I also had a version where I'm more careful with what kind of trees and so on. This goes a long way back. So it's just an upgrade of that to the infinity case.
All right. Further questions or comments, or anything else you would like to have on record regarding this topic?
Are you aware of Erik Finster's work? He did a talk a few sessions back, didn't he? He had an internal.
Can't hear the question. You have to speak up.
Can you not hear? Hello?
So the question was, I think, for Joachim, whether you're aware of Erik Finster's work, and I'm assuming it's about the optopic approach to, I guess, the fora of things.
The optopic approach.
Yeah, so the question was whether you're aware of Erik Finster's work.
Yes, I have talked with him many times, so I'm aware of it, yes.
Okay, so then I don't know, Ali, if you have a more precise question other than...
maybe I could make it more precise, but could you elaborate on that, I guess?
No, because I don't quite understand what he's doing because it's too syntactical for me. I mean, that's my fault. It's not his fault. But if I can, I mean, maybe one hint is that if you want to unravel the combinatorics of optopes, in my opinion, it's very fruitful to do it in terms of polynomial functors, because you can generate all the optopes by starting with the identity endofunctor, and then you apply the bi-Stolan construction. And at each step, you get something that's polynomial again. So that means you can describe it in terms of trees. So one description of the optopes is that there are trees decorated by trees, and so on. And this comes out quite naturally in the polynomial language. So that does not answer your question, but it just points out a connection between the polynomial theory and optopes.
So I think large part of motivation for Erik's work actually comes from the KJBM paper, if I understand correctly. So
yeah, that was
Erik is aware of.
Oh yes. So that's, I mean, that's, you use the polynomial machinery to generate the combinatorics of these shapes. But of course, that's for Erik. That's mostly graphical convenience. When he really manipulates them, he uses purely inductive stuff.
All right. Maybe then final call for questions. As far as I can tell, Joachim still has 8 pages that he can write on.
I also have unnumbered pages.
Well, I don't know if we can allow them. That's
A question. So this is from quite a few slides back now. You were talking about infinity operads and how none of the other ones have the feature.
Sorry, we can barely hear you. Is there any chance you can?
Can you not hear me at all?
Is this better?
That's wonderful.
All right.
Yes.
Sorry, yeah, you said the other models of infinity operad, they don't have the feature of having or being like monads in symmetric sequences. Is that correct?
Well, okay. It's not completely correct because after we did this work, Rune Haugseng, my collaborator, he found a version that has this feature. So there is another model that has infinity operads as monads in symmetric sequences.
All right. Anyone else? Last chance for questions. All right. Maybe in that case, I'll unmute everyone again, and we'll find Joachim again. So
Okay, maybe one more question.
Ah, man.
Okay.
You said you could compute colimits in the pre-sheaf category. Can you explain that very quickly?
Yes. Well, I don't know if I can explain it all, but it has to do with descent. So as you know, maybe the univalent.
I'll mute quickly everyone, and then I'll mute Joachim because that was.
What?
There we
Sorry?
go. Okay, we can hear you now.
Okay, so it has to do with descent, and as you probably know, many of you, well, most of you, I suppose, that the univalence axiom, when translated into category theory, is basically one of the infinity topos axioms, and it's the axiom of descent. And descent is very nice interaction between colimits and pullbacks. So, well, let me very briefly. Suppose you have a topological space U, and you have it covered by two open sets, and here you have the intersection. So that's the intersection. That also means that this is a push-out. Now, suppose you have something you want to glue. So you have something on this open set and something on this open set, and these two things agree on the overlap. That means that these squares are pullbacks. Now, what can you do to get something global? Well, you should just take the push out here, and that, by the universal property, gives you a map here. But then it's not always true that this new object you have constructed restricts to the old objects here. So this is not necessarily a pullback, and this is not necessarily a pullback. So this property that this works, that's one of the topos axioms. And with a little work, it's quite similar to the univalence axiom also. Now, when you had this, you have diagrams like this. And you would like to compute the colimits pointwise, independent of the fact that it's not a full pre-sheaf category, but it has fewer maps, because it only has those maps whose middle component here is Cartesian. But nevertheless, the very good interaction between pullbacks and colimits allow you to do it anyway. So the reason you can do this is because of descent. So that really infinity LCC.
I think we're. Did we lose? Did we lose Joachim?
No, I just finished.
Okay. Okay. Well, that's a good sign. Okay, very good. So I'm gonna ask again. Are there any questions? And now let's try to ask questions before I unmute everyone. I'll give you sufficient amount of time to do that. Okay, we're still waiting. Okay, maybe then this is it. Now I'm gonna unmute everyone and let's thank Joachim. All right. The talk is over. The record.